This video is going to be about limits at vertical asymptotes on a graph, and then just some other assorted types of limits. There's something called the sine function and limits of trig functions. So a few different topics kind of put into one video here. So the first thing that's important to know is what kind of features a graph has. So on this first function, you can tell that that denominator would be undefined at x equals 2. If we were to plug 2 into the denominator, we would get 0, which would make that entire function undefined. So that tells us that our graph has a vertical asymptote at x equals 2. There's nothing we can do algebraically to cancel out that x minus 2 on the bottom. So that informs us that the graph has a vertical asymptote. Let's contrast that with the function g of x on the right here. And also notice if I plug in a 2 to the denominator, it would be undefined at x equals 2. The function would be undefined at x equals 2, but I'm going to go ahead and factor the numerator. If I factor the numerator, I get x minus 2 times x plus 3, and I have an x minus 2 in the denominator. So when that happens, the x minus 2's can cancel, and we learn that the graph doesn't have a vertical asymptote at x equals 2. Instead, it has a hole at x equals 2. So these functions are both undefined at x equals 2, but the graph is doing two different things. On the first one, we have a vertical asymptote, something like this. And on the second one, it's just a linear function. The function x plus 3 just happens to have a hole in the graph. Okay, so on this one, the limit as x approaches 2 of our function g of x is going to exist. It's going to equal some number wherever the y value of the hole is. On this one, it looks like the limit as x approaches 2 of f of x does not exist. So we're going to explore a little bit closer what happens on the graph at a vertical asymptote and if we can get more information about the limits. So at a vertical asymptote, there's a couple of different things that can happen. So on a vertical asymptote, the one-sided limits can either approach positive infinity or they could approach negative infinity. So at the bottom of the page, I'll show you. So we might have a situation where both sides of the vertical asymptote approach infinity, or maybe one side approaches negative infinity and the other side positive infinity. And we could have both sides approaching the vertical asymptote go down toward negative infinity. So how are we going to determine what happens? So we're going to pick a number that's really close to the vertical asymptote. So in these first examples, we're going to plug in a number that's really close to 5, like 4.99. And we're picking a number that's less than 5 because, as you can see from our notation, we're doing a left-hand limit. So I'm not going to put an equal sign because this is just some scratch work. So I'm not going to say that this limit equals the scratch work. I'm just going to kind of do this work off to the side and see what happens. So we're approaching 5 from the left. So I'm going to pick a number like 4.99. Now, when we do most of these, we don't have to go all the way through and get a numerical value, but I just want to think about what's happening. If I take 4.99 minus 5, that gives me a small number. That's negative. When I divide, it ends up giving me a big number, negative 100. What if I move even closer to 5 and go 4.999? That means I'm dividing 1 by an even smaller number. And that makes my output even bigger. Well, when we find a limit, and obviously you don't have to copy down all these examples, you can just watch while I do this. When we find a limit, we're getting very, very close, arbitrarily close to 5. That means like as closer than you can even imagine. So if I do 4.99999 minus 5, that's going to give me 0.000001. And then that's going to give me a couple extra zeros here. So the closer we get to 5, the closer that this output is getting toward negative infinity. So when we divide by a smaller number, our answer is going to get bigger and bigger and bigger. So you can see in this problem, our answer is going to approach negative infinity. The closer we get to 5, the bigger the output becomes. It's negative, but it still is becoming a number that's really big in magnitude. Okay, let's look at the next one. So we're approaching 5 from the left again, but I have an X on top this time. So I'm going to think about plugging in my 4.99 to the numerator and 4.99 to the denominator. Again, the closer I get to 5, the bottom is going to get teeny. If the bottom gets really, really small, the output or the answer gets really, really big. But all we care about now is the signs. Now that we know it's going to go to either infinity or negative infinity, I'm just paying attention to what signs we have. So in the numerator, we have a negative. And then when I subtract in the denominator, I would have a negative. A negative divided by a negative is a positive. So this is going to approach positive infinity. Okay, next one. It's important to identify that we have a vertical asymptote. And we do have a vertical asymptote because there's no algebra I can do to cancel out that factor. So I'm stuck with this undefined expression because when I plug in a 5 in the denominator, I would get a 0. But again, let's just see if our graph is going to approach positive or negative infinity. So we're going to plug in that 4.99 for both x's. Now what's nice is the squared in the denominator tells me that that's always positive. And when I subtract in the numerator, it's going to be positive also. So I have a positive divided by positive. That makes my output positive. Okay, next. Again, identify that we have a vertical asymptote. So when I plug in a 5 to the denominator, I get a 0. There's no algebra I can do to cancel that out. So I'm stuck with the vertical asymptote, and we just roll with it. So we know our limit is going to approach either infinity or negative infinity, like we put here at the top of our page. Now let's just check the signs. So inputting 4.99. In the numerator, we have a positive because the square root symbol means give the positive root. In the denominator, we have a negative. A negative cubed is still negative. When we take a positive divide by a negative, it gives us a negative infinity. Okay, let's try a couple more. Okay, so now we're going to be finding limits at vertical asymptotes. And as you know, the limit is either going to approach infinity or negative infinity. We just have to check the signs. Now we are approaching an x value of -4 from the right-hand side. So we're going to pick a number a little bit greater than -4, like -3.99. So go ahead and pause the video, input the -3.99 wherever you find x, and check the sign, and then record your answer either as negative infinity or infinity. And then when you're done, resume the video and you can check your answers. So go ahead and check your answers to these 4 problems. Okay. These are a couple problems that are related to vertical asymptotes. This first one asks us to justify the number. It got cut off here a little bit at the top. That's supposed to be a 5. So in order to justify, we need to first find a left-hand limit and a right-hand limit. So I'm going to rewrite the problem, putting left-hand limit, and then I'm going to rewrite the problem, putting right-hand limit. Okay, so when we find our left-hand limit, we're going to pick something a little bit less than 3, like 2.99. And if we think about plugging in 2.99, I don't want to plug in here. I want to do my scratch work kind of below or off to the side. So if I think about plugging in 2.99 for x, so 2.99 minus 5 would give me a negative in the numerator. 2.99 minus 3 would give me a negative in the denominator. A negative divided by negative would be positive infinity. Again, you just have to recognize that this is a vertical asymptote problem, because if you input the 3 here for x, it gives you 0 on the bottom, and there's no way to cancel out that x minus 3. Finding our right-hand limit, we pick a number a little bit bigger than 3, like 3.001. Imagine plugging into the numerator, we would get a negative. Plugging into the denominator, we would get a positive. And that means our right-hand limit is negative infinity. So we're going to say that this limit, the limit as x approaches 3 of x minus 5 over x minus 3 does not exist, because the limit as x approaches 3 from the left of x minus 5 over x minus 3 does not equal the right-hand limit as x approaches 3 of our function. That's a little bit tedious and a lot to write out, but just getting some practice on justifying. You're not going to have to do a ton of these on the homework assignment, but when you are given a problem like this, make sure you do it with excellence. Okay, the next one, again, this is a vertical asymptote problem. I can tell because the denominator would give me a 0 when I plug in, and there's no algebra I can do to cancel out that factor of x minus 3. So I'm going to just show you one way to make your writing a little bit less. You can say, you can give a name to that function. So we say let f of x equal x minus 5 over x minus 3 squared. So then when we find our left-hand limit, we can just write f of x here. We find our right-hand limit, we can just write f of x here. So just like the previous problem, approaching 3 from the left, we're going to think about 2.99 and input that to get our signs. So I'm going to pause my recording, and I want you to pause, finish this problem yourself, justify, give the answer, and then resume to check your answer. So go ahead and pause the video, please. Okay, so when I found the left and the right-hand limits for both of those, I found negative infinity. And so I've made my conclusion here in the blue writing. The limit as x approaches 3 of f of x equals negative infinity, because our left-hand limit as x approaches 3 of f of x equals the right-hand limit is equal to negative infinity. Okay, so the bottom 3 problems here take into account your knowledge, or require you to take into account your knowledge of the graph of tangent of x. So graph of tangent of x has vertical asymptotes at odd multiples of pi over 2. Like negative pi over 2. Oops, positive pi over 2. 3 pi over 2. 5 pi over 2. So this is where the vertical asymptotes on this graph would lie. Actually, I'm going to move this asymptote over just a tad to make those kind of more evenly spaced. So it should be a little bit farther over like this. And that's 3 pi over 2. So the graph of tangent is going to look like this. It's going to go through the origin because the tangent of 0 is 0. It's going to pass through the x-axis at pi. And our graph is periodic. It would just continue the same pattern going off to positive infinity. So using this graph, we can find our limits. So we're finding the limit as x approaches pi over 2 from the left of tangent x. And so approaching pi over 2, here's pi over 2. Approaching from the left-hand side, our graph goes toward infinity. Approaching pi over 2 from the right-hand side, you can see if you're approaching pi over 2 from the right-hand side, the graph goes down to negative infinity. And then at pi, the limit as x approaches pi of tangent x is just going to be 0. You can just plug in there tangent of pi. That's not undefined or anything weird like that, so you can just plug in to get that limit. Okay, so this concludes our discussion of limit at vertical asymptotes. So we're going to switch gears now and look at some trig limits. So this limit, it's got sine in it, but we're not able to use the squeeze theorem. There's going to be a method that we learn later in the year called L'Hopital's rule that we will use to find this limit, but we're not able to use it yet. We don't know enough calculus. So I'm going to show you the graph of sine x over x right here. So it's undefined at the origin, or it's undefined at 0, sorry, because I have a x on the bottom of the function, and if I were to plug in a 0 there, it'd be undefined. But you can see from the table, as x approaches 0 from the left and from the right, it looks like our output gets really close to 1. You can also tell that from the graph. So approaching x from the right, or the left and the right, our graph approaches an output of 1. So this limit equals 1. If you take the reciprocal of it, it would still approach 1 as a limit. Now, any limit that looks similar to that has a limit as x approaches 0, and it has an x here in the denominator, you're basically just going to take a ratio of the argument to the denominator, and that ratio is going to give you your limit. So taking that ratio there, it just gives us 1. So this isn't like legitimate algebra I did. You can't like get rid of that sign, but you're able to find the limit by just looking at the ratio of that 100x over 100x. So I'm actually going to erase that because that was bad algebra. I don't want that equal. Looking at example B, nothing's changed except the name of our variable is now theta instead of x. So this is still going to equal 1. I told you can find this limit by taking the ratio of the argument to the denominator, and so that ratio there is just 5 over 1, or 5. D is kind of the same thing, but this constant, that it's just multiplied to the function, so you're allowed to drag that constant out in front of the limit. Now we know that the limit as x approaches 0 of sine x over x is 1, and so we get 8 times 1, or just 8. Okay, example E, taking the ratio of the argument to the denominator, that gives us 10/3. F is 0. Here's why. This doesn't fit the pattern because look, we do not have an x in the denominator, do we? All the previous problems had a variable in the denominator, this one does not. So this is just a plug it in problem. So if you plug in 0 in the numerator, that's cool. We just are not allowed to have a 0 in the denominator. But a 0 in the numerator is fine. So our answer is 0 divided by 10, or just 0. G doesn't fit the pattern either because we don't have x approaching 0. We have a pi over 2 here. So I can just plug it in. Remember, it's only trouble if we get a 0 in the denominator. That doesn't give me a 0 in the denominator. That gives me a 5 pi over 2 in the denominator. That's legit. Sine of pi over 2. Pi over 2 is right here. The y value is 1, so sine of pi over 2 is 1. Now I can clean this up by doing that baby denominator thing. So I'm going to multiply by the baby denominator of 2 on top and bottom. These denominators cancel, and then that just leaves me with a final answer of 2 over 5 pi. You don't have to clean it up. Equivalent expressions are acceptable, but I just like a more simplified answer. Okay, sometimes you have to try to see if there's something you can substitute. So on H, I don't know this limit. It's not something I have memorized. And I do know I can't plug in a 0 in the denominator. But what I'm going to do is I'm going to replace tangent 5x with sine 5x over cosine 5x. That's equivalent. Sine over cosine is tangent. I can't forget this 5x here, so I'm going to bring that over. Okay, so what I want you to see is now we have the limit as x approaches 0 of sine 5x over 5x. And then I just have this 1 over cosine 5x. All right, so we just learned that this limit we can take by doing the ratio of the argument to the denominator. So that is just going to give us 1. And I can just plug in a 0 here. Cosine of 0 is 1, and so this example H just comes out to be 1. Okay, last one. This one, again, we have to do a little bit of work. So I have limit as x approaches 0. What I'm going to do is I need some denominator of x's in order to find our limits. So what I'm going to do is I'm going to kind of do this. On the top and the bottom, I'm going to multiply by 1 over x. I'm allowed to multiply the top and the bottom of a fraction by the same thing. And then that x is just going to stick underneath here. So what I have left with is the limit as x approaches 0 of sine 7x over x over sine 5x over x. You don't have to show all this work. You can, just kind of mentally think through this. So the limit as x approaches 0 of the numerator is 7. The limit as x approaches 0 of the denominator is 5. So these are some limits of trig functions. So a similar one is this 1 minus cosine x over x. Again, I can't plug in a 0. That would make it undefined. We can't use squeeze theorem for this, but we will use L'Hopital's rule to show this later in the year. We just don't know it yet. So I'm going to look at the calculator with you. So on the calculator, you can see that it is undefined at the origin, but as x is getting close to 0 from the left and the right, the output is getting smaller. This would be 0.0005. This would be 0.00005. The closer we get to x equals 0, the closer our output also gets to 0. And you can tell that from the graph. Even though it's undefined at the origin, our limit is still going to be 0. All that we did in the numerator here is flip the order around, and all that would do is change the sign on the answer. But since 0 doesn't have a sign, that limit would also just be 0. Example K, we're going to take this and flip it over. I wonder what that would give us for a limit. Kind of would be 1 over 0, because that's what you get when you flip over 0. Let's take a look at the graph. This is the graph of x over 1 minus cosine x. So you can see as we approach 0 as an x value, our output goes to negative and positive infinity. So this one is going to be d/n(e). That kind of makes sense. 1 over 0 would be undefined. L, if you look at the numerator, all we need to do is factor out a 3 here. And then this matches the original limit in the box that I gave you. So everything circled has a limit of 0. So we can just take 3 times 0 and get an answer of 3. Okay, bottom one. If we try to plug in a 0 here, I get 1 minus 1 in the denominator, and that's a problem. So let's see what algebra we can do. I want you to think about factoring this numerator as a difference of 2 squares. So kind of like how you would factor x squared minus 9 as x minus 3, x plus 3. How would you factor that numerator? Well, we would have 1 minus cosine x, 1 plus cosine x. The denominator stays the same. Okay, we cancel out the 1 minus cosine x. And now we can just plug in. We can plug in a 0 here for x. Cosine of 0 is 1. So we're left with 1 plus 1, and so our limit is going to equal 2. Okay, the last little bit of our notes is this function here, which is called the sine function, S-I-G-N. The reason it's called the sine function is approaching 0 from the left-hand side, we have an output of -1. Approaching 0 on the right-hand side, we have a limit of +1. So this is what our graph looks like. And you know this graph because it's on your chart that you got on the second day with all the parent functions. So you should already be a little familiar with this graph. So the left-hand limit as x approaches 0 of our graph is -1. The right-hand limit as x approaches 0 of our graph is 1. Since those do not equal each other, the limit does not exist. Okay, at the bottom here, we're going to use that same function, but we're multiplying by 2. What that 2 does is it's a vertical stretch. So same graph, except the y values get doubled. Still undefined when x equals 0. So all that changes is our left-hand limit is now -2, right-hand limit is 2, and our overall limit does not exist. We could actually do this algebraically. You could pull that 2 out in front, and 2 times the limit as x approaches 0 from the left of absolute value x over x. So you could have 2 times -1 and get -2 that way. So that constant, if it's multiplied to the entire function, you can just bring it out in front of the limit and find your limit that way. This one you can't do that way. And this one has the absolute value in the denominator. It doesn't matter if that absolute value is in the numerator or denominator. It's still going to be the same graph, except this one was shifted 1 unit left. So taking our original graph, shifting it 1 unit left, like so. So our limit as x approaches -1 from the left-hand side is -1. Limit as x approaches -1 from the right-hand side is 1. We have an overall limit that does not exist because the right-hand limit does not equal the left-hand limit. So to summarize, we found limits from our sine function, S-I-G-N, sine function. We also found some limits of this limit as x approaches 0 of 1 minus cosine x over x, which equals 0, and then we did some manipulations of it. The limit as x approaches 0 of sine x over x equals 1. And when you're solving these problems, you can just take the ratio of the argument over the denominator, and that gives your limit here. And we started out with some limits at vertical asymptotes. And when you do those, you're going to select a number close to this 5, like approaching 5 from the left would be something like 4.999. And then you're just plugging in to see what sign you get on your answer. And recall, at a vertical asymptote, our limit can equal infinity or negative infinity.